So in this video, we're going to go over one of the coolest results in the course, the intermediate value theorem. I'm going to try to sketch the result as we go. So we have a continuous function f that goes from a closed interval a to b. Then we know the following thing. If we have that f of a is equal to some value up here, f of a, and f of b is some other value down here, f of b, then for every line in between f of a and b, so this is line c, there exists some point z between a and b so that f of z is exactly equal to c. Okay. So what is that really saying? It's saying that if I have a continuous function that sort of does this and goes from some point here to some point there, I can't skip over some value which is in between. I have to hit it at some point. It's obviously not true for discontinuous functions. All right, I'm going to get around to proving that later in the video, but before I do the proof, let's play with it a little bit. So the first thing that you can use the intermediate value theorem for is to prove that equations have roots, have solutions. So let's do that in a very concrete situation. Let's say f of x is equal to x to the 17 minus 3x squared plus 5x minus 1. So that's some big polynomial. I didn't cook it up beforehand, so I have no idea what the actual root is. That is any value of x so that f of x is equal to 0. But it's pretty easy to check that there exists such a value x using this theorem. So we just sort of compute immediately that f of 0 is minus 1 and f of 1 is equal to 2. And by the IVT, there exists some point x between this argument here and this argument here, so x between 0 and 1, so that f of x is 0, and that's just because 0 is between minus 1 and 2, these two values. So that's it. Very, very easy to use, and we get this sort of non-obvious fact that this polynomial has in fact a solution, at least among the reals. Okay, we can actually get substantially less obvious facts than that, using proofs that are almost as short with maybe one cute step. So here's sort of a fun result. I'm going to let f be a continuous function from S1. By S1, I mean, oops, not a very good circle. I mean just the unit circle in R2. So I have a continuous function f from that unit circle to R. Then there exists antipodal points, that is points x and minus x on opposite sides of the circle, so that f of x is actually equal to f of minus x. So that's a little bit weird, and I don't think that's terribly obvious. Certainly the first time I heard this fact, I didn't think it was obvious at all. And we're actually going to prove this using the intermediate value theorem, but we're going to have to be a little bit clever. We can't use the intermediate value theorem on f itself. We're going to have to cook up this sort of new function. So I'm looking at the unit sphere, so I think it's sort of natural to parameterize the unit sphere by an angle theta between 0 and 2 pi. And we all know how to do that. So I'm going to let g of theta be my new function from the interval 0, 2 pi to r, defined by g of theta is equal to f of cos theta sine theta minus f of cos of theta plus pi sine of theta plus pi. So what's g of theta doing? Oops. G of theta is exactly taking f at some point x and the antipodal point minus x, otherwise known as the point that you get when you rotate x through a full pi degrees, pi radians. Okay, so that's what g of theta is doing. And now we're going to take advantage of that. So if g of theta, if g of 0 is equal to 0, okay, then we're done, right? Because then g of 0 is f of some x minus f of minus x is 0, and so we get what we wanted, which is that f of x is equal to f of minus x. Okay, let's assume that g of 0 is not equal to 0. Well, then when we go through this whole thing, we notice that g of 0 is actually equal to minus g of 2 pi. So this thing we can assume without loss of generality is bigger than 0. This thing is strictly less than 0 because it's minus of the first thing. And so by the intermediate value theorem, there exists some value of theta between 0 and 2 pi so that g of theta is equal to 0. And of course, as soon as we have that angle theta is exactly the place where we find our pair x and minus x. Okay, so that's sort of a cute application of the IVT to get a result that at least I think is not terrible. So having seen some applications of the intermediate value theorem, now we're going to prove it. Actually, before I prove it, I want to sort of sketch the answer. I'm going to assume for now that the value of c that we're interested in is 0, and that f of a is strictly negative, and that f of b is strictly positive. You can do the other cases yourself. It just involves doing a few small manipulations of f, which maybe aren't so important when sketching the proof. So here's the basic idea. We're going to start off at some value, f of a, which is strictly negative. And I'm going to look at f of x for x close to a, and I'm going to trace what happens. And so since f of a is negative and f is continuous, certainly for x very close to a, f of x is going to also be negative. And so we're sort of going to wander around, and f is going to dipsy-doodle and go up and down and so on. And then at some point, since f of b is strictly positive, certainly f is going to have to jump from being strictly negative to being strictly positive at some location. And we're going to look at that place, which I'll call sort of the first crossover point. And one thing, of course, that you can imagine happening is that right before the crossover point, you're sort of strictly negative, -1. And right after that point, you're strictly positive, say +1. But of course, f is continuous, and so we're pretty sure that can't actually happen. And so our sort of candidate for this point z is going to be exactly this first crossover point. Now, of course, there might be later places as well where the value of the function is 0, but we don't really care about that. We just need to check that there's at least one point. Okay, let's add in some notation and try to make this rigorous. So like I said, I'm going to assume for now that c is 0, f of a is strictly less than 0, and f of b is strictly positive. All right, if you're worried about that, I'm going to have a little aside. What if c isn't equal to 0? Then take f of x, maybe I'll say a different function name, take g of x is f of x minus c. If f of a is equal to 0, well then of course we're just done. If f of a is greater than 0, then we can prove the following theorem that g of x is equal to minus f of x. So what I mean is the following. The reason that I can assume this without loss of generality is that if these assumptions aren't true, I can just take a slightly different function g and go through the proof with that function g, which does satisfy the requirements. And it's pretty clear for all of this that if g satisfies the intermediate value theorem, then f is going to satisfy it as well. Okay, so this is just going to make it a little bit easier to write down the proof by assuming this sort of stuff. Now I'm going to keep on going exactly the way that this sketch was going. I'm going to let S be the set of points x in AB so that f of x is strictly less than 0. So this set S is exactly the blue curve that I've drawn up here. Now by assumption, A is an S and B isn't an S, right? So that is S is not empty. And of course, it's also not the entire interval from A to B. And I'm going to let X be the supremum of the points in S. And as I said, that's somewhere between A and B. It's at least A, and it's certainly strictly less, and it's less than or equal to b. Good, actually. Now we're going to check that f of x is equal to 0, and we're going to do that by contradiction. So the first thing that we're going to consider is the possibility that f of x is strictly positive. So that is, we sort of jump immediately from being strictly less than 0 to being strictly greater than 0. So what happens if that's true, if f of x is strictly positive? Well, f is continuous, so there exists some delta greater than 0, so that for all y between x minus delta and x plus delta, the difference between f of y and f of x is small. In particular, it's less than f of x over 2. So we can do that, right, because f of x is strictly positive. We can make this difference here small, even compared to the amount that f of x goes above 0. So what happens in that little interval? Well, for y in that interval, that means that f of y is bigger than f of x over 2, which means that it's strictly positive. But that meant that actually y wasn't in the set S at all, and in fact, this entire interval is not sitting in the set S. Therefore, the supremum of S had to be actually before this interval. It's at most x minus delta. But that contradicts the fact that x was defined to be the supremum of S. Okay, so we've ruled out the possibility that f of x is strictly positive. The next thing we need to do is rule out the possibility that f of x is strictly negative, and I'm not going to go over that because it's actually essentially a copy-paste of the above theorem. I really only have to change a few places. So here, where I had f of x over 2, I now have a minus sign. A couple of places where up here I had greater than signs, I now have less than signs. Other than that, really an identical argument, so I'm not going to go over it again. And so at this point, we've ruled out the possibility that f of x is strictly positive, we've ruled out the possibility that it's strictly negative, and therefore, in fact, it must be exactly 0, which is exactly what we wanted to prove. Okay, great. I can't resist the option to play with the IVT a little bit more, so I'm going to prove a corollary, which is often called a fixed point theorem. So here's the theorem. I'm going to let f be any continuous function f from the interval 0, 1 to 0, 1. And I'm going to say there exists some point x in that interval so that f of x is equal to x. The proof of this is going to be very similar to the antipodal point theorem that I had at the beginning of the class. I'm going to define a new function g of x to be f of x minus x. And we notice the following. G of 0 is f of 0, which of course is in this interval, so it's non-negative. And g of 1 is equal to f of 1 minus 1. Well, f of 1 is less than or equal to 1, and so g of 1 is less than or equal to 0. So I have this function g that's continuous, because f is continuous, and of course x itself is continuous. And g of 0 is at least 0, g of 1 is less than or equal to 0, and so by the intermediate value theorem, there exists some intermediate value x between 0 and 1, so that g of x is actually equal to 0. But of course, g of x is also equal to f of x minus x, so that means that f of x minus x is equal to 0, and so in particular, f of x is equal to x. So a very short proof of a not terribly obvious result. And really the key part here is that f has to be mapping some set to itself. If you take that away, this sort of theorem can become very false. All right, thanks very much.